Hi everybody, this is Dr. Nigro with the notes portion for our new unit on vectors. Right, so as you can see here, I have a little thought problem for us. So imagine you are standing by your car in a parking lot. You need to meet your friends at their car, but it is on the other side of that parking lot. Your friends try to tell you where they are by giving you the following directions: 80 meters to the east and 30 meters to the north. Use the grid to map out where your friends are in the parking lot in relation to you. Draw an arrow for each direction and assume that each grid box is 10 meters. Put a star where your friends are in the lot. All right, so we are here. And if we count over 1, 2, 3, 4, 5, 6, 7, 8, and then draw our arrow, we are going to cover this distance to the east. We're then going to go to the north and we're going to travel 30 meters. So 1, 2, 3. So that's going to end here. And we're going to go up and end right there. So that ideally is where our friends are. All right, now, how do you walk to reach them? Do you walk the 80 meters east and turn and walk 30 meters north? Well, I think most people would probably say no. All right, most likely they're going to walk the diagonal between those 2 points. All right, so in other words, they're going to start, let me change colors so you can see it. They're going to start at the beginning, but instead of walking east then north, they're going to walk on this diagonal line, this blue line, all right, that I've drawn. So these three arrows are vectors, all right? So vectors are represented using an arrow, all right? And as you can see, if we look at the shape that these three arrows make, you can see this right triangle in here. So the shape of these three arrows is a right triangle. Now for us, we're going to be almost exclusively working with right triangles, but vectors can make any sort of shape. So let's say we went to the east, but instead of being directly north, the car was a little bit to the northeast. All right, so then I could draw a connector between those two that would be a more likely path that would look like this. All right, but again, I've got three vectors and they're working together to form this triangle. All right, so let's define a couple terms before we move too far. All right, so what is the magnitude of a measurement? So any measurement's magnitude is going to be that numerical value. All right, and what is the direction of any measurement? This is kind of a weird question. It's the direction. All right, but what I really mean here is we use things like north, south, east, west. Maybe we say up, down. We could say forwards, backwards, positive, negative. All right, anything that we can use to describe that direction. All right, now, two words we've heard before, scalar and then vector. So a scalar quantity, remember, is magnitude only. All right, and an example for us would be speed or distance. All right, so if we were talking about the motion of a car and we said it went 55 miles per hour, that would be an example of a scalar quantity. All right, a vector quantity, you have to have the magnitude, but you also need to include the direction. All right, so you need both of those items. All right, and an example for us is going to be velocity. All right, we've also talked about acceleration, we've talked about displacement, and eventually we're going to get to something called force. All of these are vector quantities. So an example would be that same car moving at 55 miles per hour, but we would say it's moving to the northeast. That would make that measurement a vector quantity. All right, so when we talk about a vector itself, so let's, for example, let me just draw a vector here for us. All right, here's our vector, and we're going to say it's 10 meters to the north. Oh, not well, the way I drew it is clearly not to the north. All right, I drew it to the east. So 10 meters to the east. All right, so the magnitude of the vector, again, is that numerical portion. And we represent that magnitude in the length of the arrow. All right, so maybe this particular vector I drew is 10 meters to the east. All right, but I also could draw one a little bit shorter, and maybe this one is 5 meters to the east. So the length of the arrow gives us some information. All right, the direction of the vector is the direction. All right, and that's either the angle or north, south, east, west, some descriptive word. All right, so these two vectors are both to the east, but I could also draw a vector like this, and I could say it's 30 degrees above the horizontal. So that would be another example of a direction. All right, now this last word, the resultant, that might be a new word for us. So when we draw a vector, I'm going to just redraw our car problem. All right, we have these two components, these two pieces. All right, this is our 80 meters east, and this is our 30 meters north. That path that we drew that connected these two vectors here, this is your resultant. So the resultant is always the sum of your vectors. All right, if you have a right triangle, then the resultant is the hypotenuse. I always try to spell that wrong. Okay, and since we're going to be working almost exclusively with right triangles, we're going to see the hypotenuse a lot. All right? All right. So now that we've kind of defined some terms that go along with vectors, all right, it's time to talk a little bit about how we draw them when we want to add them together. All right. So we saw in our parking lot example that vectors can be added to give this resultant vector. All right. That was the path that was most likely what we would walk to reach our friends. Adding vectors is actually pretty easy. All right. We did a lab about pennies where we mapped out a set of directions for our friends to find the penny that had the X on it. And we worked our way through those directions by going through a direction and then starting the next direction at the end of the first, and then starting the third direction at the end of the second, and we worked our way through those five directions. The resultant is the total change in your position, so where you started initially to where you end up. And the resultant vector always will start at the origin of the first vector and end at the end of the second vector. All right. When we add vectors, we always draw them tip to tail. All right. So what does that mean? All right. So let's start with a vector to the east. All right. This is the origin of both vectors. All right. For our second vector, I'm going to draw it up to the north. This is the tip, and this is the tail. All right. So when we draw our vectors, we always draw the second vector at the end of the first vector, and then we would just work our way around. Once we get to our resultant, we start at our origin, and then we draw that vector till it touches the end position, and this would be our resultant. All right. Now, what would that look like if we didn't do it tip to tail? All right. So let's say we start with this first vector again, draw it over, and instead of starting our second vector over here, we start it here. All right, so basically what we're doing is tail to tail. All right, so if I tried to draw a resultant for these, it gets a little tricky because there's no, the origin's here. So I can't reach the end. So instead, you might be tempted to draw this. Oh, that's a little crooked, but, all right, and you can see that these two, whoops, somehow I erase things. All right, my two vectors, top and bottom, put this back in here, these two resultant vectors are not the same. All right, so do not draw it any other way but tip to tail. All right, and that stands for no matter how many vectors you have. So let's say we have three vectors that we want to put together. So here's one, and here's one. All right, so we have A, B, and C. All right, so they're all tip to tail. And then when I put in our resultant, it's going to again start at the origin and go to the last position. So this would be your resultant. Okay? All right, so let's try a couple down here. All right, so we've got four vectors to work with, A, B, C, and D. And our job is to draw the two vectors that the problem tells us to do and then the resultant. All right, so let's start with our A. So A looks about like this. And if you look at B, it looks like this, and then our resultant will be the sum. So we start at our origin and we go to the end. So this is going to be A and B, and we call this A plus B. All right, now this happens to be a right triangle, but it's not always going to be that way. All right, so for example, if we look at this second set, all right, we have A again. All right, but this time C tilts a little bit like this. All right, and so if we draw a resultant here, it's the same idea. We start at the origin and we go to the end, but you can see that this is no longer a right triangle, which is fine. All right, we have A, C, and then this is A plus C. All right, and then finally, if we do a last one, all right, this one is A. Whoops, maybe I should make that a little shorter. A, and then D tilts out like this, so that when we draw that resultant, we again start at our origin and take it all the way over to the end. So this is going to be A and D, and the resultant is called A plus D. Okay? Now, what if using those same vectors, we look at A plus B versus B plus A? All right? So we again draw A first, and then starting from tip to tail, we draw B, and we put in our resultant here, and we have A, B, A plus B. All right? If we instead draw it the other way, so let's say it's B plus A. All right? So we've got B and A. The resultant still starts at your initial and goes to the origin. So we still have B, A, and we would call this B plus A. All right, so if you look at the resultant here and here, what do you notice? Well, to me, they look identical. All right, and what that means is that the order in which you add the vectors does not matter. So any order, as long as tip to tail, to tail. All right, and we saw that with our find the x activity, where it didn't matter what order we put those directions in, we were still able to reach the end position, the x. All right, so now let's talk a little bit about signs, about the direction. All right, thinking about vectors as magnitudes and directions is natural, all right, but you sometimes want to think about them as the pieces that came together to build that vector, all right? For that, we usually describe a vector not as north, south, east, west, although we will do some of that, but we usually describe them in terms of horizontal and vertical directions, all right? As always, we're going to use X to represent horizontal direction, and we're going to use Y to represent our vertical direction, all right? So the sign is what's going to tell us whether it's up, down, left, or right in terms of X and Y. So I've got two axes here. This is our Y axis and this is our X, all right? And you can also think of basically this area as, whoops, sorry. Reset, that's what I meant to do. All right, we can think about any vector that's in between X and Y in this upper area. This would be our northeastern portion. All right, this is going to have a positive Y value because it's up and a positive X value because it is to the left. All right, so over here is the left. Over here is the right. Oh, did I just mix my directions up? I did. All right, you guys will learn over time that my directions are not the best. So this is left and this is right. All right, and we're going to call this up and this will be down. All right, so if we have a vector that shows up in this northeastern corner, it's going to be positive X and positive Y. If we instead have a vector that's down in our southeast corner, all right, we're still going to have a positive X because we're over to the right, but our Y value is now going to become negative because it's down. All right. If we instead are over here and we are in our southwest quadrant, all right, now both things are negative. X is negative because it's to the left. Y is negative because it's down. And then if we end in our northwest quadrant, all right, we're going to see Y become positive because it's up, and X will be negative because it is to the left. All right, so if a vector component points up, then your Y value will be positive. If the vector component points down, then your Y value will be negative. If your vector component points to the left, your X value will be negative. And if your vector component points to the right, your X value will be positive. All right, so remember, left and right are horizontal indicators, up and down are vertical, which is why it's Y versus X. All right, now why is this important? Because if you know the components and you know the signs for them, you can place your vector within this 4-quadrant grid. All right, so let's look at what that means. All right, see, here I have 9 resultant vectors. And what I want to do is draw the right triangle, the X and Y components that led to the formation of this particular resultant. All right, so I'm going to start with A. All right, so if I look, this vector plus this vector gave me that resultant. All right, this is your X piece and this is your Y piece. So if I look, X is to the right, so it's going to be positive, and it covers 2 boxes, so it will be plus 2. Y is also going to be positive because it's up, and it covers 2 boxes as well. All right, if we move over to vector B, this resultant formed when I added this vector to this one. And so again, we have X and Y. And if we look, X is again positive because it's to the right. It covers 4 boxes. Y is positive because it's up. It covers 1. All right, we'll do this one too. So we're going to slide over, and then we're going to go up to form resultant C. And again, X and Y. And this is going to be positive 3 and positive 2. All right, now vector D is interesting. It is all vertical. There's no horizontal component here, so it's got an X component of 0. All of it, all 3, is pointed up, so a positive 3 for Y. All right, now if we look at E, we've got the opposite situation in that it points down. All right, so X is still 0. There's no horizontal piece. All right, because it points down, it's negative, and 2 because it covers 2 boxes. All right, for F, these are always hard for me to draw backwards. All right, we're going to add this component to this component. We have X and Y. All right, so we're going to get a negative X this time because it goes to the left, negative 3, and a positive 1 for Y. For G, comes over and then up. So we have X and Y, and we get positive 1 for X, positive 2 for Y. All right, now vector H is all horizontal, so our Y component will be 0 this time. And because we're pointing to the right, we have a positive and then 3 for our X piece. And then finally, I comes over and then up. So we have X and Y. Because we're moving to the left, we have a negative 1 for X. And because we're moving up, a positive 2 for Y. Okay, so this is just to kind of get us started. All right, I'm going to do a second screencast, which is going to look at the rest. All right, if you have any questions, please don't hesitate to ask.